Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the concept illustration problems which are based on specific heat. So this is the type 1 problems, and in this video we'll be going from level 1 to level 2. Level 1 is for NEET and JEE Mains, and level 2 is for JEE Advanced and Olympiads. So in this first question, you can see that Cp and Cv are the specific heats at constant pressure and constant volume. And you should note that this is not molar specific heat. This is specific heat, which is gram specific heat. And it is observed that the value of Cp minus Cv is equal to A for hydrogen gas, and the value of Cp minus Cv is equal to B for nitrogen gas. So what will be the correct relation between A and B? So we can say that obviously if Cp, we know that Cp minus Cv is equal to R, and this is the molar specific heat at constant pressure, and this will be the molar specific heat at constant volume. So this is for 1 mole. If we wish to find out the relation of Cp and Cv, where Cp and Cv are the specific heats, which is gram specific heat, and the specific heat for 1 gram, then we should divide this complete equation by the molecular mass, because we know that in 1 mole the mass present is m, molecular mass. So dividing by molecular mass, this will be Cp by m minus Cv by m will be equal to R by m. Now let us say that this is Sp, specific heat at constant pressure. Let us say that this is Sv, specific heat at constant volume, and this is some other constant R. But this capital R is the universal gas constant, and it is constant for all type of gases, ideal gases obviously. But this R is not universal gas constant, and it depends on the molecular mass. So what I am referring this Cp as Sp and this Cv as Sv. So if we find out the value of A, which is R, small r, A and B, ratio of A and B, then obviously it would be equal to mass of B upon mass of A, because this R is inversely proportional to M. So the A upon B ratio will be equal to mass of B upon mass of A, and mass of B is the molecular mass of nitrogen gas, which is 28, and mass of A is the molecular mass of hydrogen gas, which is 2. So this will be equal to 14. So the correct answer will be A is equal to 14B. So the correct answer is A. Now we move on the next problem. In this question, you can see that there is an ideal diatomic gas that is going through a process whose relationship graph between T square and V cube is a straight line passing through the origin, where T is the temperature in Kelvin and V is the volume in meter cube. So we have to find out the molar heat capacity of this process. For polytropic process, PV to the power n is equal to constant. We also know that the equation of polytropic process in terms of temperature and volume is T V ki power gamma minus 1 is constant. So in this problem, you can see that T square is proportional to V cube, and this is T is proportional to V to the power 3 by 2, and T V to the power minus 3 by 2 is equal to constant. So if we compare these two equations, then we can conclude that gamma minus 1 is equal to minus 3 by 2, and therefore gamma will be equal to 1 minus 3 by 2. So that will be 1 by 2 with a negative sign. Now we already have derived the formula of C, that C for polytropic process is Cv plus R upon 1 minus N. Okay, and N is the polytropic constant. So C will be Cv, and we know that for diatomic gas Cv is 3, in fact 5 by 2R plus R upon 1 plus 1 by 2. So this will be 5 by 2R plus 2, this is plus 2R by 3. So LCM will be 6 and it would be 15R plus 4R. So it would be 19R by 6. So the correct answer will be C, 19R by 6. Now we move on the next question. In this problem, you can see that there is a PV diagram and this is a process A, B, C, D. And there is a sample of monoatomic gas which is going through this process ABCD. We have to find out the average molar specific heat of this process, and we have to compare it with XR by 4, and we have to find out the value of X. Now this is a different type of question, and you can see that in this question there is a graph and there are 3 different processes which are combined in a graph, and we have to find out the specific heat of this complete graph. We know now we cannot establish a direct relationship between any pressure and volume or temperature or volume for this, due to the fact that there is not a single process going on. This is a isobaric process, this is a isochoric process, and this is a isobaric process again. So we cannot generalize them into a one process, and we cannot find out the polytropic coefficient. In fact, what we have to do, that first of all we have to write down, we know that dq is equal to du plus dw, and then we will write down the value of dq as nc delta t and du as ncv delta t and dw as work done. We have to find out the work done. By calculating these two, we can find out C. So this is the steps which we have to follow to find out the specific heat of this process. So first of all, let us find out the work done. So to find out the work done, we have to calculate this area, and the work done dw will be obviously the area of this rectangle, which is P naught into 2V naught, 2 P naught V naught, plus the area of this small rectangle, which is V naught into P naught. So it is P naught V naught. So dw will be equal to 3 P naught V naught. This is the work done. Now let us find out the temperature at A. So temperature at A will be P naught into 2 V naught by Nr, and temperature at D will be 6 P naught V naught upon Nr. So delta T is Td minus Ta, and hence delta T can be written as 4 P naught V naught upon Nr. Okay, and we have to calculate the value of this. So N is not given and C we have to find out. So it is 4 P naught V naught upon Nr. Now let us use the next page. It would be better. So you can see now that dq is nc delta t, and that is ncv delta t plus dw. Now n is n, c is c, and delta t is 4 P naught V naught by Nr. So it is 4 P naught V naught by Nr, and this is N, and the gas is monoatomic gas. So for monoatomic gas, CV is 3 by 2 R and delta T is 4 P0 V0 by NR. And the work done in this process will be 3 P0 V0. So this is plus 3 P0 V0. So cancelling out N with N, so you can see that we can also cancel out P0 V0 with P0 V0. So 4C by R will be equal to, this is 6, this cancelling N with N, R with R. So this is 6 plus this would be 3. So this is 9 and C will be equal to 9R by 4. So the value of X will be equal to 9. Now we move on the next problem. In this question, you can see that there is a graph which is plotted between specific heat C of a solid as a function of temperature T in Kelvin. This specific heat is continuously increasing from 0 to 500 Kelvin, and the rate of increment of temperature is constant. It is given that dT by dt is constant. Okay, and we have to choose the correct expression. Now we can, in the first question, first option, the rate at which heat is absorbed in the range of 0 to 100 Kelvin is varying linearly with temperature. You can see that till this point this graph is approximately linear, and dq is equal to, or we can say that q will be equal to nc dt. So dq by dt will be equal to nc dt by dt. This is a constant, let us suppose k. So dq by dt will be equal to nc into k. Now in the range 0 to 100, C is increasing linearly with temperature. Therefore we can say that dq by dt, rate at which heat is absorbed, is increasing linearly with temperature. So A option is correct. Heat absorbed is in increasing the temperature from 0 to 100 is less than the heat absorbed for increasing the temperature from 400 to 500 Kelvin. So you know that if specific heat is higher, then more amount of heat will be required to increase the temperature by the same range. So in the region of 0 to 100, specific heat is lower, and in the region of 400 to 500, specific heat is higher. So the heat absorbed in increasing the temperature between 0 to 100 will be obviously less than the heat absorbed in increasing the temperature from 400 to 500, because specific heat in this range is higher. So B is also correct. There is no change in the rate of absorption of heat in the range of 400 to 500. So approximately we can consider that this graph is almost constant in this range. So we can say that C is constant and dq by dt is constant in the range of 400 to 500 Kelvin. So C is also correct. And rate of absorption increases in the range of 200 to 300. Obviously you can see that in this range C is increasing, so rate of absorption will be increasing. So D is also correct. So the correct answers of this question are A, B, C, D. Now we move on the next question. In this question, you can see that 1 mole of hydrogen gas, which is assumed to be ideal, is adiabatically expanded from initial state P1 V1 T1 to the final state P2 V2 T2. Then we have to find out the decrease in internal energy of the gas during this process. So we can see that obviously during adiabatic process dq is 0, and therefore du plus dw will be 0. So du will be equal to minus of dw, and this negative sign shows that if work done is positive, that is in expansion, the change in internal energy would be negative. So du will be minus of work done. Work done will be n, we can say that obviously if gas is expanded, then volume V2 will be greater than V1, and therefore we know that internal energy will be decreased, therefore temperature T2 will be less than T1. So the change in internal energy delta U will be obviously equal to N CV delta T, which is T1 minus T2, because we have to find out the decrease in energy. So decrease in energy should be constant, and N is 1, so this is CV into T1 minus T2. So the correct answer will be A. Now we move on the next question. In this question, you can see that 1 mole of an ideal gas, which is undergoing a process P is equal to alpha T to the power half, where alpha is a constant. We have to find out the molar specific heat of this gas. So we know that P is equal to alpha into T, alpha T to the power half. And if we can write down T as PV by NR, so we can see that P will be proportional to P to the power half V to the power half, and P to the power half will be proportional to V to the power half. So you can see that P will be proportional to V, and P V to the power minus 1 will be equal to constant. So if we compare this equation with polytropic process, then we can say that N will be equal to minus 1. So C is CV plus R upon 1 minus N, and CV is R upon gamma minus 1, and this is R upon 1 minus N, and N is minus 1, so it would be 2. So C will be equal to R upon gamma minus 1 plus R by 2. So taking common 2 and gamma minus 1, this is LCM. So this is 2R plus R into gamma minus 1. So you can see that it would be equal to, C will be equal to R common gamma plus 1 upon 2 into gamma minus 1. So the correct answer will be C. Now let us move on the next question. In this question, you can see that we have to find the number of atoms in a molecule of a gas for which the ratio of specific heats at constant pressure and constant volume becomes 25 by 21 times if the rotational degree of freedoms of the molecules are frozen. Which means that originally, let us see, that originally if gamma was 1 plus 2 by F, where F is the total degree of freedom, in which there are rotational as well as translational degree of freedoms. But if the translational degree of freedom are frozen, then in fact rotational degree of freedom are frozen, then the new gamma would be 25 by 21 times of old gamma. And new gamma will be equal to 1 plus 2 by 3, because if rotational degrees of freedom are frozen, then the only degree of freedom which are left will be translational. So 1 plus 2 by 3 will be equal to 25 by 21 of gamma, which was initially 1 plus 2 by F. So this would be equal to 5 by 3, and that is 25 by 21 1 plus 2 by f, and this is 5 and this is 7. So 7 by 5 will be equal to 1 plus 2 by f, and 2 by f will be equal to 2 by 5. So f will be equal to 5, and this gas will be the diatomic gas. Diatomic gas. And therefore in diatomic gas there are 2 atoms in a molecule. So the correct answer will be 2. Now we move on the next question. In this question you can see that 1 mole of an ideal monoatomic gas is taken along this process, in which PV to the power x is constant. This is a polytropic process, and we have to find out the values of C dash and x dash in this graph. So we already know that polytropic process has C is equal to CV plus R upon 1 minus N, and in the place of N it would be X in this case. Okay, so CV is 3 by 2 R for monoatomic gas, so C will be 3 by 2 R, plus this would be R upon 1 minus X. Now at X is equal to X dash, at X is equal to X dash, C is 0. So you can see that this term will be 0 obviously when CV, we know that when it is equal to minus CV, when R upon 1 minus X will be equal to minus CV. So R upon 1 minus X will be equal to minus of R upon gamma minus 1, and therefore X will be equal to gamma, and gamma for the monoatomic gas will be equal to 5 by 3. So value of X dash will be equal to gamma, which is 5 by 3. And again we can see that B will be the correct answer, but let us also find out the C dash. So C dash will be the value of C when X will be 0. So when X will be 0, C will be equal to 3 by 2 R plus R. So C will be equal to 5 by 2 R. So the correct answer will be B. Now let's move on the next question. In this question you can see that there is a graph between CV and temperature for a gas that is ideal gas, and CV is changing like this. So we have to find out the work done in or we have to find out the heat supplied at constant pressure in raising the temperature of this gas from 200 Kelvin to 400 Kelvin, and number of moles is 1. So let us see that 200 Kelvin will be somewhere around this point and 400 Kelvin will be somewhere around this point. Let us suppose that this value is y1 and this value is y2. So we can easily find out the y1. So we can say that this is 5 by 2 minus 3 by 2. So this is 1, and 1 upon, we are equating the angle. So I am taking this tan theta. So this this height is 1 and this is 200. 1 upon 200 will be equal to 5 by 2. This is 5 by 2 minus y1 upon this is equal to, this is 200. So it would be equal to 200 minus 250 minus 200, that is 50. So 5 by 2 minus y1 will be equal to 1 by 4. So you can see that y1 will be equal to 5 by 2 minus 1 by 4. So y1 will be equal to 9 by 4. Okay, now let us find out y2 by the similar method. So you can see that this is 1, again 1 upon 100, because it is 450 minus 350 is equal to, this will be 3.5 r, which is and this is y1 is also 9 r by 4, so obviously r would be there. So this is 3.5, which is 7 by 2 minus y2 divided by, this is 400, so it would be 50. So 7 by 2 minus y2 will be equal to 1 by 2, and y2 will be equal to 7 by 2 minus 1 by 2, so it would be 3. So y2 would be equal to 3r. Okay, now let us see that the area of this graph will be CV dt, small area, and the heat supplied at constant volume is change in internal energy, it is N CV dt, and N is 1. So du will be the area of this complete graph from this range to this range. Okay, so area of this complete graph will be sum of A1, this is A2, and this is A3. So let us find out A1. So A1 will be equal to the area of trapezium. So area of trapezium will be half sum of parallel sides into height. The parallel sides are this 5 by 2 plus 9 by 4 into height is 50. So it would be half 5 by 2 plus 9 by 4 into 50. So A1 will be equal to, this is 25 into 19 by 4. Now A2 is this area, so A2 will be equal to 5 by 2 into this is 5 by 2 and this is 100. So A2 will be equal to 5 by 2 into 100. Okay, so 5 by 2 into 100, and there will be a r also. So it would be equal to 250 r. And A3, let us find out A3. So A3 will be the area of this graph, this one. So it would be half y2 plus 5 by 2, and y2 is 3r. So this would be half y2 is 3r plus 5 by 2 r into this length. This is 50. So this would be equal to 25 into this would be 6 plus 5, which is 11 r by 2. So the total area A will be du, and du will be equal to A1 plus A2 plus A3. So it would be 25 into 19 by 4 plus 25 into 11 by 2 plus 250 r. So this would be 22 plus 19, and it would be equal to 41 into 25 by 4, 41 into 25 by 4 plus 250. Now 41 into 25 is 1025 plus 250 into 4 is 1000 divided by 4. So it would be equal to 2025 divided by 4. Okay, so this is delta U. Now if we need to find out, if we wish to find out dW, so dW at constant pressure is PdV, and PdV is nR delta T. N is 1, R is R, and delta T will be 400 minus 200. So it would be 200. So dq will be equal to 1025 upon 4, in fact 2025 upon 4 plus 200 into r. So it would be equal to 2825 upon 4r. So this will be the value of heat supplied to the gas to increase the temperature from 200 to 400 Kelvin at constant pressure. Now we move on the next question. In this question, you can see that the ratio of a specific heat for an ideal gas is Cp by Cv, which is equal to gamma, and this gas undergoes a polytropic process in which Pv to the power gamma is constant. So we have to find out the values of N for which temperature of the gas increases when the gas rejects the heat to the surroundings, which means that the specific heat of the gas is negative. And we have already studied this concept in the last video of the laws of thermodynamics, which was with the name of negative specific heat. And we have seen that in that video we studied that N should be greater than 1 and N should be less than gamma. So N should be between gamma and 1. So if N is between gamma and 1, then the specific heat of the gas would be negative. Now we move on the next question. You can refer to that video if you want to refer. Now we move on the next question. In this question, you can see that an ideal gas is going through this process in which T is equal to T naught e to the power alpha V, where T is its absolute temperature and V is its volume, and T naught and alpha are constants. So we have to find out its molar specific heat for this process if the molar specific heat is Cv, and we have to express the answer as a function of volume. So obviously, first of all, let us see that T is equal to T naught e to the power alpha V. Now dt will be equal to T naught alpha e to the power alpha V into dV. Now we know that du is n Cv dt. So du will be equal to n Cv into dt will be T naught alpha e to the power alpha V dV, and dW will be the work done, which is P dV. Now we know that PV is equal to nRT is valid for this. So P will be equal to nRT by V. So P will be equal to nRT, and T is T naught e to the power alpha V divided by V. So work done will be equal to nRT naught e to the power alpha V divided by V into dV. And we know that dq is equal to du plus dw. So now we know that dq is nc dt, and again if we substitute the value of dt as T naught alpha dv into e to the power alpha v, so this is nc T naught alpha into e to the power alpha v dv, and dq is equal to nc T naught alpha e to the power alpha v dv will be equal to du plus dw, and du is this ncv T naught alpha ncv T naught alpha e to the power alpha v into dv plus work done will be equal to this one nr T naught by v e to the power alpha v dv, nr T naught by v e to the power alpha v dv. Now let us cancel out n T naught e to the power alpha v and dv, n T naught e to the power alpha v and dv, and it would be c into alpha is equal to cv into alpha plus R by V. So C will be equal to CV plus R by V alpha. This will be the specific heat of this process. Now let's move on the next question. In this question, you can see that there are several graphs which are plotted between P and V for a polytropic process on an ideal gas, which is PV to the power K is equal to constant. We have to find out the value of K for which the specific heat becomes Cp plus Cv by 2. So first of all, let us see that for any polytropic process, C is equal to, let us write down the value of C. So C is equal to Cv plus R upon 1 minus X or K in this case. So if C is Cp plus Cv by 2, so it is Cp plus Cv by 2, and this is Cv plus R upon 1 minus K. So this is Cp minus Cv by 2, and this is R upon 1 minus K. Okay, and this Cp minus Cv is R, so R by 2 is R upon 1 minus K. So 1 minus K will be equal to 2 and K will be equal to minus 1. So this process represents the specific heat as Cp plus Cv by 2. And we also have to find out the value of K for which the specific heat is Cp plus Cv. So if C is equal to Cp plus Cv, then Cp plus Cv is equal to Cv plus R upon 1 minus K. So cancelling Cv, Cp is equal to R upon 1 minus K, and this gas is a monoatomic gas. It is specified in the question. So the value of Cp for a monoatomic gas is 5 by 2R. So this is 5 by 2R. Therefore 1 minus K can be written as 2 by 5, which is equal to 0.4, and K will be equal to 0.6. So if K is equal to 0.6, then C will be equal to Cp plus Cv. And for K is equal to 0.6, this graph would be lying between these two graphs, like that. Still it would be a hyperbola, but it would be lying between these two graphs. So this was it. And in this video complete, we have seen that what are the different types of questions which are being asked on specific heats, and this is a very important video, and I am again and again reminding you all that please don't miss concept illustration problems, because they will let you understand the real concept in depth. Okay, so please do not miss these videos. Thank you.